Hello everyone, and welcome to the Institute of Physics East Midlands Branch Featured Talk 2021. My name is Rebecca Dewey, and I'm the chair of the branch committee. We organise these featured talks each year and have recently hosted speakers such as theoretical physicist and science communicator Jim Al-Khalili, professor and author of the book The Physics of Superheroes, Jim Kakalios, writer, comedian and broadcaster Tamandra Harkness, and lifelong contributor to the field of astrophysics, Professor Dame Jocelyn Bell-Bonnell. We usually host our featured talks in person, touring around various parts of the East Midlands. But due to the obvious, our plans have changed somewhat this year. We're absolutely thrilled to take advantage of the new situation and bring this lecture to so many more people, spanning a much wider geographical range, and all from the comfort of our and your own homes. The virtual nature of communications of late has also given us the exciting opportunity to bring you speakers who are geographically nowhere near us, as we have done today. Professor Sheila Rowan is Director of the University of Glasgow's Institute of Gravitational Research and holds the Chair of Natural Philosophy there. Sheila also became the President of the Institute of Physics this year. While working between Glasgow and Stanford universities, Professor Rowan's work has contributed to a significant improvement in the sensitivity of the Laser Interferometer Gravitational-Wave Observatory, otherwise known as LIGO, and other detectors. This has been in part due to a new method of suspending the detector mirrors using fused silica fibres that was developed by Sheila and her colleagues and implemented in numerous detectors across a consortium of groups working across the UK and the US, led by Sheila's team at the University of Glasgow. One of the most high-profile outcomes of the team's work was itself one of the most significant scientific breakthroughs of this century, the first gravitational detection of gravitational waves, announced in February 2016. So I'm super excited to be introducing Sheila tonight to give her talk entitled Gravitational Waves, What We Have Learned and What's Coming Next. For anyone else who would like to receive this lecture in British Sign Language, we have two BSL interpreters, Judy and Max, signing for you this evening. You can click the View button in the top right-hand corner and select Side-by-Side Gallery, which will allow you to use the sliding bar to make the interpreter or the speaker bigger or smaller. You can also choose to hide non-video participants from the same menu, and it'll hide any presenters and organisers who do not have their videos on. If you would like to receive the transcripts, the captions for the video this evening, please click the button at the bottom of your screen that says CC Live Transcript. There you can show or hide subtitles or change the subtitle settings. There will be an opportunity for me to read out some of your questions at the end, so please get your questions coming in the chat. If you want to ask a question by speaking or by signing, please raise your hand at the end of the lecture. If you want to have your video on to sign a question, please say so in the chat when you raise your hand, and we'll make you a panelist so that you can ask your question. This lecture and the BSL interpretation will be recorded and posted online on the Institute of Physics YouTube channel for future access. At the end of the lecture, when you leave, there will be an exit questionnaire. Please fill this in for us if you can, as it's really valuable information for us. Anyway, that's all the housekeeping done. Over to you, Sheila.
Oh, Rebecca, thank you very much indeed, both for that invitation, that introduction, and also for the invitation to speak today. And it's an absolute pleasure to be here. So hopefully you've seen the abstract, the advert, and the title here. I'm going to talk about gravitational waves, what we have learned, and indeed what we think and hope is coming next. And to give you a bit of a forward look, this is what I'm hoping to cover in the talk this evening. I will talk a little bit about what the nature is of gravitational waves, what they actually physically are. I'm also going to talk a bit about the instrumental challenges leading to that first detection of gravitational waves, tell you where we are with our current results, and some of you may have seen there was a news announcement of new results just over the last week or so, and then give you the forward look, what's coming on the near horizon, and actually our longer term vision for some of the excitement and the science that's still to come. So to start then, what are gravitational waves? To understand that, we have to think a little bit about what gravity is, or how we picture, how we envisage gravity. For many years, and again, what folks are often taught at school, we had Newton's theory of gravity. And Newton tells us, in terms of gravity, if we have two objects, some distance apart, each of those objects has some mass, those objects feel an attractive force. They feel a force pulling them together. That's the force that holds us on the surface of the Earth in this picture. And that force we think of as gravity. The strength of the force of gravity depends on the masses of the objects and how far apart they are. And that theory works extremely well. It works extremely well in many situations, and we still use that formalism for many useful things. However, it has a feature that's rather uncomfortable. Since the size of the attractive force that these objects feel depends on their distance, their separation, if that separation changes, the force that they feel changes. And in Newton's theory, it changes instantly as soon as the separation changes. In the limit, if one of those objects thus is, say, here on the surface of the Earth, and the other one is a star on the other side of the universe, in principle there's an attractive force. If the separation of that star and the Earth changes, then that information would be known instantly, because in Newton's theory, that's how the force of gravity depends on separation. Separation changes and the force changes instantly. Well, that feels uncomfortable, it feels wrong, and in fact, special relativity, Einstein's theory of special relativity, tells us that no information, and that includes gravitational information, can be carried, transmitted faster than the speed of light. So actually, special relativity tells us there must be traveling gravitational signals across the universe. There must be gravitational radiation. It took general relativity, again, Einstein excelled himself with the theory of general relativity, to put that picture of gravity on a mathematical footing. Though here we're not going to look at the mathematics. We can, fortunately, use the fact that general relativity gives us a picture of what gravity is in Einstein's theory. So if you imagine, first of all, our universe is an empty place. There are no masses in it. There's nothing there. Imagine a flat sheet with a grid on it. That's our empty universe. We come along and we add an object to our universe. In this case, in our cartoon here, we add a planet, and it curves the space around it. Our flat sort of sheet now starts to curve because of the mass that's been added. You can then imagine if we add a second object to our universe, it will appear to be attracted to the first. It will roll down that curvature in space-time. So in that picture, in that image of general relativity, the curvature in space caused by mass, truly in space-time, that curvature is gravity. You can imagine now if our objects move, if what we would say is the distribution of mass changes, but imagine our objects rolling around in our rubber universe here, the curvature changes. That change in curvature is a change in the gravitational field. And as those objects move, those changes in curvature ripple out across our rubber sheet, and those are our traveling gravitational signals, our gravitational waves. So that's the simplified picture of what gravitational waves are: ripples in the curvature of space caused, truly space-time, caused by the movement of mass. Now that was a sort of 2D picture of a flat universe. Imagine now we have a sort of tube of space, distances in space. See, there's our grid this time. We've made a tube. A gravitational wave traveling down the middle of that would cause this time the sort of shape of space to change in a very characteristic way. So imagine that's a cylinder originally. A gravitational wave passing through it stretches distances in one direction and simultaneously squashes them at right angles to that. So that's, remember, a gravitational wave traveling down the middle. So in scientific language, we say that gravitational waves are produced by a changing distribution of mass. That's our objects moving in the universe. They travel away from whatever produced them at the speed of light, prediction of GR, general relativity, and they change the effective distance between points at right angles to the direction of travel. Now, when we want to measure that effect, what we do is we effectively take a slice through our cylinder here. Imagine that as our grid again, our flat grid on your screen. And we look at the effect of gravitational waves in changing the distances of points on that grid. And you can see for something that's originally a circle, distances are stretched in one direction and squashed at right angles to that. And that oscillates, that switches back and forward. We get this oscillating change in distances. The waves stretch and then shrink distances. So how do we then detect that? We use something called a laser interferometer. What we do is we take light from a laser, we split it into two we call it a beam splitter, effectively a half silver plate. Half the light goes in one direction, half the light goes in the other direction. It bounces off mirrors. Those mirrors are our markers that we've put down and whose position we're going to measure. Light bounces off those mirrors, comes back and adds up at the beam splitter again. We look to see what the beam splitter looks like. Is it bright or dark? Because remember, light is a wave, disappears, this wave goes out along the arms, bounces off the mirrors and comes back. If the positions of those mirrors are the same, the light wave that comes back can have two peaks perhaps that add up and give a bright spot. If a gravitational wave has come along, passed through our detector, stretched one arm and squashed the other, say, so that in one arm the light's coming back in a peak, in the other arm the light's coming back in a trough, and they cancel out, we get a dark spot. So by looking at the brightness of the spot at the output of the interferometer, we can see, have the mirrors moved? Now the trouble is, they haven't, even with the sort of biggest signals we can hope to detect, they haven't moved very much. And we can estimate how much we expect them to move. So imagine one of the original arm lengths in our device here has some length L, and a typical gravitational wave moves it by some small amount that we'll call here delta L. We can calculate from general relativity, from knowing sort of big masses far out, out in the universe moving, how much, what the size of effect is that we expect. We call that the gravitational wave size or amplitude h, which is twice the change in the length of an arm, twice the mirror movement divided by the original length of the arm. General relativity tells us that that is 10 to the minus 22. I'll give you a feel for what that means in a minute. If we rearrange this, and I promise this is the only equation in the talk, if we rearrange that, the amount that a mirror moves, we can see is the strength of the gravitational wave roughly times the length of the arm. So if we built a device, a detector, in our laboratory on a tabletop, made it about 1 meter in size, our mirrors would only be moving 10 to the minus 22 meters or less. What size is that? That's less, it's less than 1,000th of the size of a subatomic particle. It's a tiny, tiny amount. So we don't build 1 meter detectors, we make L very big, and that magnifies up the effect that we're trying to measure. It enhances the signal that we're trying to detect, and that is why we build very big observatories. We don't make them small, we don't put them on a tabletop. So what sort of things might produce gravitational waves that are big enough for us to detect? Well, the sort of densest objects that we can think of with the strongest gravity that we can think of are objects called black holes. So black holes are the endpoints of the life cycle of stars that have used all their fuel, they've burned their fuel, they're not producing energy that can hold them up any longer against the force of gravity that's trying to make them collapse. The cores of those stars collapses in, blows off the outside, and the center collapses down into a region of space where gravity is so strong that nothing can escape its pull, not even light. So we give them the name black holes. So you've got a little animation here that showed 2 black holes spiraling round and eventually merging so that a new black hole is born. And it's one of the things that we believe should produce gravitational waves. So I'm going to run this animation again, because you'll see as those black holes, and you can see the sort of animation showing the dents that they're causing in space-time, as they spiral round one another, they've been caught in one another's gravity, they're producing gravitational waves. And underneath, at the bottom of this animation, you can see a wavy line that is showing the signal, the gravitational wave effect that we would expect to detect here on the surface of the Earth. As these black holes get closer and closer, the signal gets faster and faster as they spiral in, it gets larger and larger, until eventually, when these black holes smash into one another, the gravitational wave signal reaches a maximum, a peak, a new black hole is born, and then it wobbles slightly and settles down. And the signature of that event, that characteristic signature, is then sent out across the universe, these changes in the curvature of space-time, these ripples, for us to pick up here on the surface of the Earth. And indeed, that is what happened. Again, on 14th September 2015, we picked up a gravitational wave signal with our detectors here on Earth. You can see here this little animation showing that gravitational wave signal arriving, causing Earth to wobble slightly. You will notice that the slide says scale of effect vastly exaggerated. This is a tiny effect, remember. Everything's moving. Our markers, our mirrors are moving less than 1,000th of the size of a subatomic particle, tiny effect. But that gravitational wave did arrive, pass through us and our observatories here on Earth, and then carry on its way out through space, 14th September 2015. And when we looked at the signal picked up by our observatories, you can see it had a very characteristic shape. If you look at the center pattern here, that looks very much like the signal that we saw from the animation, from the simulation of the signal of 2 black holes colliding. And such a signal was picked up in 2 gravitational wave observatories that were running, and one in Hanford in Washington State, one in Livingston in Louisiana, the LIGO observatories. And from the exact shape of that signal, the way, the frequency that our mirrors shook at, and how that shaking changed, we can deduce the properties of what produced the signal. So the signal is allowing us to do astronomy and astrophysics in a very different way. We can tell that it was two black holes colliding, had to be two black holes. We can tell how far away they were when they collided, about 1.3 billion light years away, where, remember, a light year is a distance. It's the distance that light travels in a year. We can tell that the final black hole that was produced when the original two smashed into one another was about the size of Iceland, but it was about 62 times the mass of the sun compressed into that size. That it was spinning, the final black hole, about 100 times a second, so that a point on its circumference was traveling at nearly half the speed of light. And we get all that information from the shape of the signal that you can see on the screen there. To give you a little bit more of a feel, this is a very different way of doing astronomy. These were black holes. They produced no light when they smashed into one another, as far as we can tell. So we visualize this in a very different way. If you look at the scale along the bottom here, this was over in half a second. And from here to here is half a second. The signal shot through our observatories. And the bottom panel here is just a different way to visualize this signal. Again, it's time along the bottom. Up the side here, you'll see is frequency. So that's again the rate at which our mirrors were oscillating. And the color tells you the size of the signal. So for these kind of events, we get this very characteristic sort of visualization. See, it's a very different way to do astronomy. And all that information is embedded in the shape. And remember, this is a tiny motion. We've built very sensitive instruments to do this, tiny, tiny motion. So these observatories then are different than we think of when we think of telescopes that we point. Remember, they look very different. You can see here is a picture, an aerial picture of the LIGO Observatory in Hanford. And here is an aerial picture of the one in Livingston in Louisiana. And you can see this very characteristic L shape, again, of the instruments, the central building there to give you some feels about the size of a supermarket. And these arms are 4 kilometers long. These are large observatories. Whilst they are jointly managed by Caltech and MIT, again, the instrument science involved actually was partly developed by scientists around the globe, including here in the UK. And the science that's done using these instruments is also, again, done by a large collaboration. So much of the work that I will talk about today has been done by a collaboration of more than 1,000 scientists all working together. It's the work of many, many people. So you can see, to give you again a bit more of a feel for what these sites look like, show you just a quick video clip and an aerial view of both of the observatories. So this is the Hanford Observatory. It's the central building with the laser looking down one of the arms. And this is the Livingston Observatory, nominally an identical observatory, but in a very different site. This is, of course, in Louisiana, where you can see it's actually in a swampy area. You can see the trees and the pools along the interferometer arms, and it's very beautiful actually to visit. So inside these instruments, I showed you the simple version early on. Of course, to build instruments that are capable of making these very sensitive measurements requires significant technology. So I'll give you just an overview of some of that to give you a feel for the sorts of technology that's inside those giant infrastructures. Well, we start off, of course, with light from a laser, a high-power laser, which is a continuous wave laser operating in the infrared. That light is conditioned and then sent into, there's our L-shape interferometer. We, rather than just having 2 mirrors at the ends of the interferometer arms, we actually have additional mirrors here close to the beam splitter to form cavities to bounce the light many times in the interferometer arms. And these components on the whole are carefully isolated from all sources of external disturbance. And what are the sorts of disturbances that can cause us problems? Well, remember, we're trying to measure the positions of mirrors. If those mirrors were just placed on the ground, seismic noise, ground motion would be a problem for us. And that can be caused from everything from just people walking past causing the ground to shake, to the fact that even if you are in the middle of a continent, the ground actually at quite low frequencies moves. There's something called the microseismic peak, and it moves as a result of waves beating on the ocean shore a long way away. And so you see that even in the middle of a continent. We're trying to detect gravitational waves on the whole at frequencies between about 10 Hertz and 1000 Hertz. So seismic noise is an issue at the low frequency end of that. And in these particular observatories, the LIGO observatories, we have platforms which are servo controlled. They're electronic control systems that keep them stable to try and reduce the effect of ground motion on our mirrors at low frequencies. In addition to those active platforms, there are more stages of isolation, passive stages. Which go on top of the active stages. And again, the pictures here are just to show you what some of these look like. There's an active platform, and the mirrors will sit on top of that version. Some of the other components, there are active platforms and the mirrors are suspended from them. At high frequencies this time, up towards the kilohertz end and the hundreds of hertz, there's a different source of noise that troubles us, and that comes from the fact that we're using laser light to do our sensing. So I said earlier that you can think of laser light as being a wave. We send out light waves along our arms. You can of course think of light also as a stream of particles, of photons. Our detector works, as I told you earlier, from looking at the brightness of the light at the output of the detector. So we have a sensor, a photodiode that measures the intensity of the light. At high frequencies, there are counting statistics, what we call shot noise, in terms of the number of photons counted, that start to produce statistics that looks like a noise source to us. We can reduce the effect of that by actually using more photons, by turning up the laser power. However, if we do that, remember that stream of photons, every one is bouncing off our mirrors. So there are many, many photons bouncing off our mirrors. Each of those photons has some momentum. So when it bounces off the mirror, it actually transfers some momentum to the mirror. And that we call radiation pressure, the photons buffeting actually our mirrors. And there's a balance between those two noise sources, in fact, which sets a limit to the sensitivity of these kinds of instruments that is equivalent to what you get if you apply the Heisenberg uncertainty principle, fundamental quantum limits to measurement. So even though we've built very big detectors, we actually can eventually be troubled by quantum effects. The laser I mentioned is very high power. That was a contribution from colleagues in Germany. So this is an international collaboration. It's a roughly 200 watt laser contributed by the Max Planck Albert Einstein Institute. So we've isolated from seismic noise. We've got lots of laser power. What else do we have to worry about? Well, it turns out for our mirrors, each atom or molecule in those mirrors is itself shaking with thermal noise. Just the fact it's at room temperature means the atoms and mirrors vibrate slightly. And Rebecca mentioned at the beginning, one of the contributions from the UK was actually around minimising thermal noise in the instruments. The amount of thermal noise that we have depends on the material that we choose for the mirrors itself, and to some extent the size and shape of them. So we make them from fused silica. Again, it's like picking a good wine glass. You ping it and you hear a very pure note that tells you that the energy is being stored in a particular frequency range, a particular note. We use the same principle and we choose that frequency at which our vibrations would be concentrated to be away from the frequencies that we want to detect gravitational waves. And we go further than making the mirror from fused silica. We make the suspension fibers from fused silica. Remember, these are large observatories. So the mirrors that we're talking about here are about 40 kilograms. They have to survive the buffeting of those and not be too affected by the buffeting from the photons that are bouncing off them. So we want them to be quite heavy. So each mirror weighs about 40 kilograms, suspended on 4 fused silica fibers, which are a few hundred microns each, which is about a few times the thickness of a human hair. And surprisingly, those fibers can be very strong. People think of glass fibers as very delicate. Well, they can be, but actually, if handled correctly, they can be stronger than steel. So we've worked from the seismic isolation, we then suspend these mirrors very, very carefully. The mirrors themselves are crucial to the instrument because they are both the marker that the gravitational wave moves, whose position we're sensing, but they are also optical elements. They are the mirrors that from which light is bounced off in our cavities. And there are very tight optical requirements. What those mirrors have to be, they have to not absorb much laser light. They have to have low absorption and are custom designed with very, very low absorption properties. But even so, even with the best fused silica we can buy and the best coatings that we can make, the amount of laser light that we're shining on them, some of that is still absorbed, and that actually causes the mirrors to thermally deform. We have to compensate for that, which is done in a number of ways. You can see here we have what's called a radiative ring heater. You can think of that as a big toaster in a ring, applying heat in such a way as to undo the deformation caused by the absorption of the laser light. And then that's for low order deformations. For more complicated deformations, again, there are other ways in which that is compensated for. So I've talked in some detail about the LIGO observatories, but they are actually part of an international network of observatories. They're physically located in the United States. There is a slightly smaller detector, 3 kilometers long, located in Italy, the Virgo instrument, which is again a combination of countries, France, Italy, the Netherlands and others who are involved in Virgo. There's a smaller detector. We in the UK are involved specifically in LIGO, but also in a detector called GEO, located in Germany, which has tested many of the technologies that are now in the larger instruments. There's also a detector in Japan, the Kagra detector, and in future, we hope, in fact, there will be a third LIGO-like instrument in India, LIGO India, which form separate collaborations, but actually working closely together. Because to do the science, to actually do the astronomy and astrophysics, you want a network of gravitational wave detectors. 1 or even 2 doesn't do everything that you would really like. And why is that? Well, I said these are not like telescopes that you point and look at a portion of the sky with. These are more like microphones. They're picking up vibrations from almost any direction. And that has advantages and disadvantages. The disadvantages, it makes it harder to know where in the universe your gravitational waves have come from. So we do that by timing when a signal arrives first at one instrument. Here you can imagine a signal arriving first at the Livingston instrument and a bit later at Hanford, and that would tell you the direction that the signal must have come from. Two instruments gives you some information, but actually you want more if you really want to pinpoint where on the sky a signal has come from. So in these plots here, what you can see are each of these lower plots is a picture of the sky. It's a model of the sky, sort of unwrapped and put on the page. And in this first picture, the blue ellipses are telling you the accuracy with which you would be able to determine where a gravitational wave had come from associated with that portion of the sky. If you had 3 detector sites, you'll see even with 3 detectors, there are some portions of the sky to which you have no sensitivity to gravitational waves. You simply wouldn't know that a signal had come from there. If you go to 5 sites, like the model I gave you earlier, with one in Hanford, in Livingston, one in Japan, and with Virgo, that uncertainty shrinks and you do much better in being able to tell where in the sky a signal has come from. And as we'll see, that's an important thing to want to be able to do. So I talked about the first detection that happened in our first observing run. You can see here 01, in which LIGO was running. There was a second observing run in 2017 in which LIGO was running and in which Virgo then joined. And I'll show you, and that was a very exciting observing run, and Virgo joining made quite a big difference. And from it came a number of gravitational wave signals. So, excuse me, you will see here a number of coloured dots. So let me try and interpret those for you. Up the side, you will see numbers from 1 to 80. That's number of times the mass of the sun, solar masses. The blue circles that you can see here are black holes where LIGO has detected the gravitational wave signals from pairs of black holes colliding. And so here you'll see a 20 solar mass black hole and a sort of 35 or so solar mass black hole that we have found that have spiraled in, collided and formed a new black hole. So you'll see there's a set of these signals. The purple dots are individual black holes for comparison that we believe existed from seeing how electromagnetic signals moved around those. And down here you'll see something different. This time not black holes colliding, but these orange dots here you can see are neutron stars colliding. So neutron stars are the other end point of a star that has collapsed just before a black hole has formed. We get to a neutron star. And so we detected the first neutron star collision in the observing run. And importantly, because we had a third instrument running, the Virgo instrument was running, we could see that that source was localized to a sky region of about 28 degrees. That was important because it meant that those people with telescopes could point them to that region of the sky. Because neutron stars, unlike black holes, are made of real matter, of real stuff that when it collides produces light. In this case, produced what we call gamma rays, very short wavelengths light. And you can see here one of these plots where we have time along the bottom, frequency up the side. There's our gravitational wave signal. And a couple of seconds after that, there was a burst detected of electromagnetic radiation in gamma rays. After 2 seconds, there was that gamma ray burst. After about 10 to 11 hours, there was an optical signal detected, what we call a kilonova, and then a whole series of detections of electromagnetic light this time. And that allows us to do a remarkable amount of science. So one of the things in the title of the talk was what have we learned? Well, from this one event, this one detection of colliding neutron stars, we detected a significant amount. It confirmed that colliding neutron stars are a cause of short gamma ray bursts. People had been detecting these gamma ray signals and not really understanding where they were coming from. For the first time, we had evidence it's colliding neutron stars. We have a measurement for the first time of the speed of gravitational waves compared with the speed of light. Remember, the end of the gravitational wave signal was just 2 seconds before the arrival of the gamma ray burst. We can tell from the signal that the distance to this event this time was about 130 million light years. So we know that gravitational waves travel at the same speed as light does, to an accuracy of about 2 seconds in 130 million years. We got information about the rate at which the universe is expanding from the gravitational wave signal. It's a very specific measurement that can be done. Again, I won't go through the whole list here, but for the last one, we have confirmation of, for the first time, where some of the heavy elements in the universe are coming from. So this is a periodic table, which you might recognize from chemistry at school, and it's color coded to tell us where the individual elements are being produced. And we see some of them, again, are produced very early in the universe, in Big Bang fusion. And some of them are produced, we think, in supernovae, but some of them, in orange here, we know from looking at the light that was detected when the neutron stars collided, some of them are being produced when neutron stars collide. And in particular, I think the ones that caught people's imagination with platinum and gold. So that lovely artist's illustration of 2 neutron stars colliding, you can see the gold and silver there, and I think that's probably why it's on the front page of the Financial Times, because they thought the readers would be interested. And all of that we got from that gravitational wave detection. So you can see there were a series of observing runs, again 01, 02, and now of course we have the third observing run, which was split into 2 parts. And between those, we stopped, and often stopped for some period, and then turned on again. And when we stopped, we were working on the technology of the detectors to improve their sensitivity. And it's worth us doing that. You can see from this plot here, we've sort of have the sort of cumulative number of candidate events up the side. So for 01 and 02, that increased relatively slowly, but when we got to the third observing run, it shot up because we had improved the performance of our instruments. So the most recent announcement over the last couple of weeks was of a large number of new detections from that third observing run. So our catalogue of gravitational wave signals is now up to around 90. Again, and that increases, of course, the science that we can do. In there, again, I won't talk about it in detail, but there's the discovery throughout this of what are called intermediate mass black holes of above about 100 times the mass of our sun, that people had believed existed, but this is the first time we had detected evidence of them. In there were also black holes eating neutron stars, which again had been theorized to happen, but our detections showed these for the first time. And so there's a whole set of new science that we start to be able to do with this number of detections. So to bring you right up to date, we're off at the moment, improving the detectors again, and there will be, we hope, an observing run 04 coming in mid-December 2022, again with improved sensitivity. So what's coming in the short term? I won't talk about this in detail, but we can see further ways to improve the technology beyond even that plan for the 4th observing run to make our instruments more sensitive. Beyond that, we start to think about things that are not possible in our current infrastructures, for which we might need to build whole new observatories. In Europe, that's a process that started some time ago. There's back in 2008, I think, there was the original design study for what's called the Einstein Telescope, a conceptual design for an even bigger gravitational wave detector, most recently updated in Europe. And there are a couple of sites, perhaps even 3, under consideration for where that might go. Would be underground to help reduce further the seismic noise, and this time with 10-kilometer arms and even bigger instruments. So there's a lot of work ongoing there. And in the US, there's a parallel study for a detector called Cosmic Explorer, this time 40-kilometer long arms, but above ground, a slightly different design. In each case, though, the improved sensitivity lets us study a larger volume of our universe. So the plot here, to help you interpret it, if you imagine we here on the Earth are at the middle of this plot, all the yellow dots here are colliding pairs of neutron stars, and the white dots are colliding pairs of black holes, about 30 times the mass of our sun. As we improve the sensitivity of our instruments, again, looking to the last couple that I described there, we get to the point where we can envisage ways in which we could detect all the colliding black holes that there are out there in the universe, with this sort of future vision. And there's a whole set of science, and I touched on some of this earlier, that then can be done once we have those kinds of capabilities. Understanding what neutron stars are actually made of, what really is the material in there. They're quite mysterious objects. Testing extremely strong gravity eventually is general relativity, the right theory of gravity. And understanding where these pairs of black holes and neutron stars formed and how they formed. And all of that is still to come. So we hope in future, we will get to a point where we not only have the detector network that I've talked about, LIGO, Virgo, CAGRA, but actually added to that, the Einstein Telescope, Cosmic Explorer, and in the 2030s, even a space-based gravitational wave detector, LISA, to detect sources of gravitational waves that the ground-based instruments won't be sensitive to, because we believe there's a whole further set of science and signals out there that we would like to see. So just to finish, I've talked about the technology that has gone into detecting gravitational waves, but we actually work quite hard in thinking about how that technology and how spin-offs of it can be used not to do astrophysics, but actually to improve people's lives here on Earth in a much shorter time scale. And so these are just examples from my own group in Glasgow, working with colleagues at other universities in Strathclyde and actually in other fields, and colleagues who are biologists, looking at applications in healthcare, in the environment, and understanding our geophysical world. So in short, although we've spent a fair amount of time talking about things that are dark, I think the future for gravitational waves is bright. And I'll stop there.
Thank you so much, Sheila. That was a really brilliant, exciting and fascinating talk. I really, really enjoyed that, so thank you. So now we're going to turn to the audience. Please get your questions coming in the chat. And if you want to ask a question by speaking or signing, please raise your hand at the end, as we're now at the end of the lecture. And if you want to have your video on to sign a question, please say so in the chat when you raise your hand. And we'll ask you to become a panelist so that you can ask your question. So we've had several questions coming into the chat already, and I'll try and merge a few of them together so that hopefully we can get them answered quite comprehensively. So this one came in, really intrigued me. If you were past the event horizon observing the merger of two black holes, what would you experience? How would you feel these gravitational waves? Would there be radiation, or yeah, are you able to expand on that?
So it's an interesting question. So people sometimes do ask, so I'll say a little bit about this. So first of all, even if you've just got one black hole, if you get closer and closer to it, what happens to you, what you feel, depends actually to some extent on the size of the black hole. If it's a huge black hole, supermassive black hole, the event, you actually pass the event horizon without too much difficulty. Space-time's curving sort of shallowly, and you sort of pass the event horizon, and actually before you've probably realized it, you're past the event horizon. You have passed the point of no return. As you get a bit further in, then space-time starts to curve more, and you start to get a bit stretched, and things go badly wrong. If it's a small black hole, actually you start to feel that head to toe stretching because it's got a sort of sharper curvature. You feel that a bit sooner. In terms of gravitational waves, actually the gravitational wave signals are not the bit that causes you problems, that wobbling of the gravitational waves, that curvature in space-time. The bit that does you the damage and the bit you need to worry about is typically the static curvature, that head-to-toe stretch from the existence of the black holes themselves. So the gravitational wave is a perturbation. It's just a little change on the static background.
Okay, brilliant, thank you. Okay, so I've got another question here. Do gravity waves suffer from redshift, say if the universe is expanding between the emission of the wave and its detection? And how does this energy loss process work, if so? So
redshift, we do worry about redshift, and that's taken into account when we do the analysis of our signals. Can you ask the second part of that about energy?
And so if does that redshift directly correspond to an energy loss? Does it what's the physics of that redshift process?
So the gravitational waves are, I think in this case, stretched in the way that you would normally think of that. I'm not sure about how to answer the energy part of that question, I confess, so I'm not going to try, just in case. No,
that's great. An honest scientist. We all have to sometimes say that's just not something we've encountered.
Just to make sure I answered it correctly.
Thank you. So couple of questions, and also you mentioned it yourself about how these huge multidisciplinary science and engineering projects prompt the development of new technologies that often get reappropriated in completely different aspects of science, or even in everyday life. You mentioned healthcare and the environment. Are there other areas, and could you tell us a bit more information about those?
Certainly. So I'll talk a little bit about the examples on the slide there. In terms of healthcare, there's a couple of examples, one of which is working with cell biologists who study stem cells, and stem cells are special because they can, in principle, turn into any cell in the body. And so one of my colleagues, Stuart Reid, has been working with colleagues looking at preferentially enabling stem cells to turn into bone cells, and doing so applying our techniques developed for producing vibrations and controlling vibrations, and applying those vibrations in a particular manner to stem cells, preferentially making them into bone cells. And that is of interest. If you can do that, if you can speed up the production of bone cells, it has potential applications in treating people who are suffering from osteoporosis, and in helping helping with bone transplants, where people need transplanted bone, which it turns out is the second most transplanted thing after blood. Another one is in, you'll see there was a picture on that slide of the retina, and there's a company who, now a multinational company, who make machines that scan the retina and image it to look for diseases. And actually, it's one of my colleagues in Glasgow, Seong Heng, who works on data analysis techniques, has been working with that company to help automate some of the processes that they use actually. For instance, and it turns out to be surprisingly difficult to tell a left eye from a right eye, but they've been using machine learning techniques to automate some of that, which speeds up the ability, in the end, the ability to treat people. And so those are just a couple of examples.
That's brilliant. Thank you very much. So there's a couple of questions about the sort of 3 to 4 dimensional sort of shift, and in terms of thinking of tacking on a 4th dimension. Is that literally time? How can we think about that, and how does that affect how we're thinking about black holes in a 4th dimension?
So I'm not, again, it's a question I'm not quite sure how to answer. We often, other than to say, we often talk about gravitational waves curving space, but in truth, what we're talking about is space-time, is space and time. But I think there's not an easy way to give you a fast answer to that question, I think.
Okay, thanks. Again, just proving how you're very, very honest. So thank you very much. I've got a question about black holes and neutron stars being talking about sort of ordinary matter.
Yeah.
Does dark matter or dark energy do similar things? Does that collapse also?
So it's very interesting. So dark matter is a very interesting one. There are, after our first detection, one of the things that happened was people thought hard about how signatures of dark matter might show up in gravitational wave signals, and there are some papers that talk about that, there are also interesting aspects of, because we simply don't know what dark matter is. So there's been quite a bit of work looking at whether some of the things that we've been calling dark matter actually might be in black holes. In other words, are there more small black holes out there than we've been thinking of? Because there were many, I kind of said we detected gravitational waves and it was 2 black holes colliding, but actually there were many surprises about that detection. The eagle-eyed amongst you might have noticed when I talked about the sensitivity and the capabilities of our observatories, it actually often talks about the sensitivity in terms of the distance to which we could detect 2 neutron stars colliding. And that's because before we made a first detection, we tended to think that the things we would detect would be colliding neutron stars, and that's because from conventional electromagnetic astronomy, we'd seen pairs of neutron stars, so we at least knew they existed. There were pairs of neutron stars out there. We really didn't know if there were going to be pairs of black holes out there, and the size of the black holes that we actually detected were actually a bit bigger than we expected. And so a whole new set of interesting thoughts opened up for people, including, could some of the contribution to dark matter actually be coming from black holes? So there's a bit of controversy around that, and I think people probably think not. However, it has been a very interesting science area to actually have some of those discussions and you know, give a new perspective possibly on some aspects of dark matter.
Lovely, thank you. There's a question here, is there an explanation for the 2-second difference between gamma and gravitational waves? Does gravity wave propagation get slowed down by intervening mass, or does the gamma ray propagation get influenced by gravity wave space-time distortion?
So in terms of, so it's 1.7 seconds, and I think what people think is probably the case is that 1.7 seconds is actually real, it's physical. In other words, you can imagine the gravitational waves being produced as the neutron stars spiral round, and then they have to smash into one another. And if you imagine, I have animations of this, but I didn't put one in the talk. If you imagine them colliding, the gravitational waves signal actually disappears, because remember, that's from the two stars moving. When they smash into one another, that gravitational wave signal gets smaller. It actually goes to quite high frequency, and it takes time. You've got nuclear reactions happening as the individual, sort of the matter of those two neutron stars smashes into one another, and then undergoes a series of nuclear reactions, producing electromagnetic radiation. So that 1.7 seconds, it probably takes some time for the nuclear reactions to get to the point where the emission happens. So it's not necessarily an indication, in fact, that they're traveling at different speeds. It simply could be the physical time it takes to go from them smashing into one another to producing a gamma ray burst. In terms of how gravitational waves are affected by passing through things, well, the truth is they're not affected very much, and it's both a pro and a con, again, in terms of doing gravitational wave science. The upsides of that are that by the time gravitational waves reach us, they really have not been affected much by anything between us and what produced them. And it's why they provide that signature of the objects that produce them. Unlike light that can be absorbed by dust or easily obscured, the gravitational waves pass through. So that's a positive. On the other hand, it's a negative in that because gravitational waves don't interact with much, that makes them very hard to detect. It's why we have to work so hard to build anything that can be affected by the gravitational waves enough for us to measure it.
Lovely, thank you. A question here about the graviton. How do gravitational waves fit in with the particle model?
Yeah. So again, for those folks who might be wondering, the graviton is the sort of theoretical particle that people believe should exist associated with the gravitational field, because the other forces and fields get their particles. So we have photons, again, for light. However, gravitational waves, any gravitational wave that we detected would really be equivalent to a huge number of gravitons. So we are not, with our gravitational wave detectors, going to detect individual gravitons. We're not going to do that. But they are, you can think of them as equivalent to many gravitons.
Cool, thank you. There's a few questions I'm going to try and merge together about the detector sort of geometry and design. So talking about as detectors get larger, longer arm length, is there any sort of time resolution degradation as a result of them being so big, and then how do you use that to work out how far away you are from the source?
So those are slightly different things. So as you make the arms bigger, you in the first instance are more sensitive to gravitational waves. But then if you make them too big, the effect of a gravitational wave starts to get washed out, because and it's to do with the effectively the time it takes light to travel. So there is actually an optimum size for any gravitational wave frequency. There's actually an optimum size of detector. We put arm cavities, as I mentioned, in the arms of our gravitational wave detectors to store the light, which is kind of a bit like making them longer. We'd store the light for longer. But if you make them too big, you can eventually wash out the gravitational wave signal again, but that's beyond where we are. in terms of, so it sounded like the second part of that question was about directional sensitivity again.
Okay,
but
yeah.
That really we get from the baseline, the separation of the individual gravitational wave detectors. So in fact, what we want is gravitational wave detectors well separated around the Earth. Now we do pretty well because we've got 2 across the United States, 1 in Europe. But if you looked at the sort of plot that I showed of the Earth with the location of those instruments, actually you would spot they're mostly in the, I think they're all in the northern hemisphere. If we and some of my colleagues have done studies, theoretical studies, to say, well, where would be the optimum place to put another gravitational wave detector if we had to add one to the network? And when you do that and you account for the parts that are watery, so we can't put a detector there, and you look at the landmass, Australia would be a good place to put another gravitational wave detector. Again, so they're well separated to improve the timing resolution between the instruments.
And what about in space?
So in space, so it's a little bit different. So there we are proposing to, in fact, there's a mission called LISA, the Laser Interferometer Space Antenna, which would be 3 spacecraft in a triangle. And those spacecraft, instead of being separated by a few kilometers, would be separated by sort of more than 1 million kilometers. Inside each of those spacecraft would actually be a free floating object, a cube. So instead of our mirrors, we have these cubes which form our markers. Around those, they're freely floating. Around those, we put a spacecraft, which to some extent protects that cube from external disturbances, from the solar wind. And there's laser sensing that would go between those spacecraft, but you can't do what we do on Earth, which is put a mirror and reflect the laser light back, because you've put your laser on your spacecraft, you've sent it out, and no matter how sort of, carefully you point your beam to start with, it starts to diverge. So over the baselines that we're talking about, only a tiny amount of light arrives at the far end. So we don't reflect that back, it's detected, and we use a different kind of scheme to monitor the relative separation of the spacecraft. Those spacecraft go into an orbit, what's called a heliocentric orbit. They follow the Earth round as the Earth goes around the Sun in a constellation, and we look for lower frequency gravitational wave signals. This time, signals at frequencies well below what we could detect on the surface of the Earth. And the reason we go to space, so I talked about seismic motion, which is the ground shaking and troubling our mirrors on the Earth. But there's another source of noise called gravity gradient noise, which comes from the fact that you can't shield against gravity. And remember Newton from back at slide number 2. If you've got 2 objects that have some separation, they feel a gravitational pull. So people just walking past or carefully suspended test masses exert a gravitational pull on them and cause them to move. Now people only walk slowly. They don't run 100 times a second back and forward past their test masses. So it's a low frequency effect. You can't shield against it, but what you can do is put your detectors in space where there aren't moving people or trucks or even changes in atmospheric pressure. The density of the air column can start to exert a gravitational pull, and that goes away if you put things in space.
And so all of that together, how does that affect the sensitivity of those detectors?
So the detectors in space, I think if you look at the raw sensitivity, is actually a bit lower than the detectors on Earth, but they have a longer baseline and large signals. So it's not quite the right thing to exactly compare the sensitivities. It's a very different frequency band and with different sources, because this time instead of black holes that are tens of times the mass of our sun, LISA might detect supermassive black holes that we believe are at the centre of galaxies. Two galaxies colliding and with supermassive black holes at their centre, with those supermassive black holes spiralling around to collapse. It's a very different source, a very different frequency range of gravitational wave signals than we would detect here on the surface of the Earth. So it's a kind of different thing.
Okay, cool, thank you. One here, I think, from the theorists in the audience. How have your observations contributed to understanding of relativity, special general relativity, and quantum mechanics, and perhaps even unification theories?
Sure. So one of the things our observations have done is rule out a whole, there's something called MOND, so modified Newtonian gravity, so the whole set of gravitational theories there, which sometimes have been sort of used as an alternative explanation for the effects that we sometimes allocate to dark matter. So that binary neutron star event, where we detected that and we detected the electromagnetic signals, the implications of those combined detections actually ruled out a whole class of MOND theories of modified Newtonian gravity. So, I mean, that's certainly one place where the gravitational wave observations have affected theoretical predictions and theoretical studies.
Anything at the quantum level?
At the quantum level, so that is so where quantum is an effect for us is actually in our detectors. So I talked about the fact that we have shot noise and radiation pressure, and for any frequency, you can think of a light power at which there's a sort of relative minimizing of those two effects, which coincides with the limit to position that you would get set by applying the uncertainty principle to measuring the position of a particular mass delta x, delta p greater than or equal to h bar up and 2. So that is very interesting, and there's a lot of work done on understanding the quantum behavior of the optomechanics in these observatories, and in fact how to get below the standard quantum limit. And so there's a whole set of work done there in understanding how to physically build these observatories in such a way that you can get below the limit that you would believe is set by the uncertainty principle.
Okay, thank you. How frequent are these events that produce gravitational waves? So
we, more frequent than certainly we thought to start with, particularly the collisions of black holes. I think after the first set of detections, we could tell that a pair of black holes was colliding somewhere in the universe about once every 15 minutes, we thought. So, wow. Yeah, indeed, we've somewhere out there, something went bump in the night several times during this lecture.
Do you think galaxies doing the same thing will be as frequent, more frequent, less frequent?
So there's a range of theoretical predictions. They are less frequent, I believe, but again, a lot depends on the exact models, and it's why I think much less frequent, but it's why observations will tell us a lot.
Yeah, brilliant. Could you talk a little bit about the computer simulations of the different waves from different kinds of sources? Are you able to use computer simulations to sort of guess or predict what the source is of something that you're detecting?
Yes, so I didn't talk actually about the analysis side much, but there's a lot of work on that side of things, and it's just, I'm an experimenter, so I've talked quite a bit about the experimental side, but there's a whole set of people who do sort of numerical relativity and simulations of these kinds of events, and who construct templates for what the gravitational wave signals might look like from different kinds of collisions, for black holes of different sizes colliding, excuse me, black holes, whether or not they're spinning, whether one's spinning, both are spinning, are the spins aligned? And so there's a whole family of templates of candidate signals, which the exact shape of which depends on the properties of the object. And so there's a huge amount of work, yes, goes into that.
Cool, thank you. This one here, does the motion of the moon around the Earth or any sort of planetary motion, how does that impact on the signals that you detect?
So the motion, the effect of the moon is a really interesting one. The gravitational wave signals from that, the straight gravitational wave signals, be too small again for us to detect. However, the moon, of course, has a straight gravitational pull, and it actually can, at low frequencies, again, not frequencies where we're trying to detect the traveling gravitational wave signals, but tidal effects can affect the overall behavior of the instrument. And so it is something that we think about, even although it doesn't produce gravitational wave signals for us to detect, but it does exert, as you know, there are tides, and so it does exert a pull that sometimes we have to consider.
Thank you. There's several questions that have gone back to touch on the black hole merger process, when two black holes merge together. What causes them to lose their energy so that their orbits degrade and merge? And how can you detect something that's coming out of them? Surely nothing should be able to get out of a black hole. So sure. How are we going against this principle?
So we're not, that's the first thing, we're not detecting things from inside the event horizon. What we are detecting are the disturbances of space-time from around the colliding black holes, and they are radiating energy through gravitational waves, through the energy that goes into distorting space-time around the black holes.
Thank you. Oh, I just saw one there and then it moved. How much do these things cost?
So that's a very good question. So I think they are, as you might imagine, not cheap. It is big science. I think the initial LIGO observatories, and I would have to check, but I think of the order of $200 million. And it's, you know, I've forgotten, I confess, the exact amount for the advanced LIGO upgrade in the UK. Again, I can tell you the numbers because we were partners, and I think the UK was about £8 or £9 million that went into our contribution, which was, of course, the suspensions and the design and the supply of that. So it is big science.
Big science, lovely. This one's an intriguing question. Why are these detectors constructed in L shapes, not as a triangle?
Well, you can see LISA, again, maybe is planned as a triangle. The L shape for the ground-based instruments, well, you can see that is matched well to the fundamental distortion in space produced by a gravitational waves. And we had at the beginning, remember, it squashes in one direction whilst it simultaneously stretches in another. So that L shape is very well matched to that. Of course, something in a triangle means that you do still pick up that effect. It's just not, well, it depends exactly on the direction of the gravitational wave. The effect I described is for a gravitational wave going into the plane of the detector. So a triangle, you know, it does have some advantages, but the L shape on the ground, I think, was the simplest one that's well matched to the distortion, the fundamental distortion.
Brilliant, thank you. So one here about the human scientist. When did you first realise that you wanted to either move into science or to become a gravitational waves investigator. What first got you into this field, or were there other bits of science that you spent time on? Yeah, just tell us a bit about your career path, I suppose.
Sure. So I always was interested in studying physics, and in particular the bits of physics that related to understanding our universe. The fact I found it fascinating as a child that you could ask questions without too much difficulty that no one knew the answer to. Where did it all come from? How far out does the universe go? It's actually quite easy to ask questions people don't really know the answer to as a child, and I found that amazing. You could quite quickly get to those, and I thought that would be really, really fascinating to work in. I became hooked by the gravitational waves field at university. I studied physics as an undergraduate, and between my penultimate year and my final year, I did a summer project with what was then the Gravitational Waves group in Glasgow. So I did a 6-week project and worked with the group, and was kind of hooked at that point when I realised you could work in a lab, you know, working on some of the experimental sides of things, and be part of this much bigger goal. So it wasn't just, you know, an individual scientist doing things, it was being part of a team with a really big aim, which was to make the first detection of these gravitational waves predicted by Einstein, had been predicted back in 1916. And so there was this sort of, you know, global hunt, this global sort of challenge with different teams in different countries sort of working to try and build instruments to make this first detection. So it was the combination for me of being able to do something practical to contribute to what felt like a very big, exciting sort of goal, one of those questions, this sort of unconfirmed prediction.
Thank you. And I think actually it's also come in the chat, but I was going to ask, or I was going to ask it anyway. How, any advice for someone wanting to get into this field now? How could they start out? How do you get to work at something like LIGO, or whatever the new LIGO is going to be in 15 years' time?
So the good news is there's lots of ways and lots of skills that are needed, and so you could be involved in a whole number of different ways. So we do astrophysics. So if you're coming and you know some computer science, we need people who understand, you know, how to do efficient large-scale computing. So computing, we need computing people. We need people who know about lasers. We need people who know about materials. We need people who know about electronics. We need people who know about civil engineering. I mean, I talked about these future detectors, and I quickly skipped over the fact that there's a lot of studies being done of the sites. We need people who understand about boreholes and seismic measurements and mines and giant boring machines, and, you know, almost any branch of physics and engineering that you can think of in computing science. We need people who can help us do the outreach. There's just a huge number of ways. So if people want to get involved, I think there's any number of skills that we need.
Lovely. Well, that's a great note to end on. Thank you so much. So that just leaves me with the task of thanking you very much, Professor Sheila Rowan, one more time, and also thanking our British Sign Language interpreters for all of their hard work during the evening. I hope you found this lecture interesting, engaging, intriguing, or at least that it's got you thinking about a different area of physics. Thank you so much to the audience as well for attending this talk and for your really probing questions. Please keep a lookout for more events from the East Midlands branch of the IOP and from the Institute of Physics more generally. The next event the East Midlands branch is likely to be hosting is the 3-Minute Wonder, which is going to be in the spring, and we're hoping to do that in person. So keep an eye out for that. So thanks everyone again, and I wish you a lovely rest of the evening.